In this lesson, we'll take a look at how to create complex physics bodies in order to accommodate concave shapes. We have a series of objects, here planetary bodies, falling into a basket, and you can see the planetary bodies within the baskets here through the slats. So we'll create a complex physics body for the basket and then spawn the planetary bodies so that they fall within the basket. Let's get started. Normally, when you attach a physics body to an object, it'll simply attach a rectangle around the bounds of the object. So here you can see the basket redrawn with just a simple rectangular physics body, and none of the objects appear to fall through because the uppermost boundary of the object is the top of the basket. And so there isn't a way for the objects to appear as if they're going into the basket. And these outlines of the objects are turned on by setting the draw mode of the physics engine to hybrid, which we've covered in a previous movie. So what we're going to do is we're going to map out a custom physics body using Illustrator in order to get the points of a polygon or multiple polygons that will be pieced together. The result of this will be a physics body comprised of 3 parts, and you can see here there are 2 arms and a base, and the objects will be able to drop into the basket, and the player, it will appear to the player that the objects are within the basket, and putting them behind the basket is simply going to be a matter of using groups and specifying the drawing order of the objects. So I've opened the basket within Illustrator, and you can use any program that will allow you to draw polygons and get the XY coordinates of the points of the polygon. I just happen to have Illustrator. And what you want to do is you want to take your object when it's imported, and if you're using Retina images, you want to import the smaller size, because remember, that's the dimensions that will actually be used. So you import your object, or your image, and you want to center it at the top left because the display is 0, 0 at the top left. So I have my object locked here at 0, 0, and I'll go ahead and lock the layer, and now I'll create a polygon or a couple of polygons to represent the boundaries that need to be in place for this object. So what I like to do is start with a simple rectangle and then adjust the points. Let me color this a bit differently. And now I'll use the tool here, the direct selection tool, and simply start dragging points around. For this particular lesson, I won't be too accurate. And this is a pretty time-consuming process when you do this method. So I've got one arm, and I'll copy it and paste it. And let me transform that and flip it. And now I'll draw the base. Okay, so those 3 polygons will represent our physics bodies. Now, here's where it gets really time-consuming. You have to define each polygon point by point, and your polygons can have only a maximum of 6 points. So what you do is you select the point of one particular polygon, and let's zoom in so we can really get a good look. So you select a point. Here I'm using the direct selection tool, and you can see that a tooltip has appeared that gives me the X and Y of that point. Now you don't want to deal with fractional points. You want actually whole numbers. So this negative 137.8, when I go into Corona, I'm just going to type negative 138. I'll end up rounding them. It doesn't make a huge difference, but if you've got a pretty complex physics body, then you're going to want to make sure that you are drawing the polygons to whole numbers. And what we'll do is we'll capture each point in clockwise order. Okay, and when we write them in Corona, we'll write 0.1, 0.2, 0.3, and 0.4, but we won't go back to 0.1 as 0.5. We'll just simply write the 4 points. This takes quite a bit of time. I recommend pencil and paper when you're doing this so that you can just write these points down. I'm actually going to write them down, magically have them appear when we start writing our code. I've already written a fair amount of code for our tutorial. I'll go over it before we start creating the complex physics body. At the top are our constants that are in every video. I've cached the math.random function here in a custom table. And this is, of course, essential. I have started the physics engine, and I've set the draw mode to hybrid. And if you want to take off or disable the draw mode so that it's just normal, you can comment that out. Or if you just want to show the physics bodies, we can type debug. But I want to show hybrid. There are no vars yet, probably won't be in this particular case. This is a template I use for my own projects, no classes. I've created 4 groups. There is the scene group, which is the group that all of the other groups are stored in. If you've seen any of the game tutorials, this is the group that we would use with the director class. Sometimes I call it local group. And then I've got 3 other groups, a background group, a planets group, and a basket group. I insert the background, planets, and basket into the scene. And then I've got some constructor code for creating the basket and the planets. Now, I do it this way because I want the flexibility of creating baskets or planets on the fly, and this is easily transportable to a module if I wanted, but the tutorial is so small, I'll just keep it in line with this code. So to create a new basket, I define a group within this basket constructor, and then define a local variable that represents the basket body, the image, and position that within the local group here, G. And it's important that I return that group because later I am going to call this particular method, and it's got to return a display object. Now we'll be inserting our custom physics bodies here just before insert, and after we do all of our insertion, it's good to set the reference point for the group, because remember, it is the group that is being returned and body is within that group, to the center reference point. So we'll come back to this particular constructor. It's the one where all of the action is going to happen. Now I've got another constructor here, new planet, and it's the same MO as the previous constructor. Create a group local to this constructor. And I've got 3 different types of planets. And so the essence of the group is that using this variable ball, I am creating new images drawn from this image table. Now, if you step backwards, this will make sense. This image variable is the string images / concatenated with the results of the planets table. So then go back. You can see n is a random number between 1 and 3. Which means that the planets table, having 3 indexes, we will randomly draw one of the planets within the time here. Sorry about that. So I've got the Earth, Sun, and Moon, and then I've defined a radius. We need to do that because we are going to attach circular physics bodies to them. And what I'm essentially doing is I'm randomly drawing from the planets table and looking at the image property of that planets table. Afterwards, we are attaching a standard physics body. So here we're adding the body. Notice that we're adding it to the group and not to the object, and that's pretty critical. If we were to add it to the object, what you would notice is that the balls would fall down and they would not interact with the basket at all. Because it is the group that is returned, we need to add the body to the group. It's the highest most object in the stack. So we add the body before we insert the ball. You'll notice that if you start to mess with the order of when these bodies are added before or after the insertion into the group, you're going to notice some really strange results. So here we're adding the body to the group and defining a few of the properties, a bounce of 0.3, and then most importantly, a radius. When you define the radius property, then it will apply a circular physics body. We insert the ball into the local group, and then set its reference point and return the group. So that is the planet constructor. Okay, so after we have definition of our constructors, we just do some pretty routine things. We'll define a background image, which is just a rectangle that has its opacity set to 255 via the set fill color. I prefer to set the opacity that way rather than using the alpha property. It's centered in the screen. Now then I insert that background image into the background group and then define some physics boundaries so that if the planets fall and hit the ground and go to the left or right, they don't go off screen. They will bounce against walls and the ground. So I've defined ground, left wall, and right wall. These are all standard rectangles, and I have positioned them accordingly. Finally, I've added physics bodies to those objects, and these are added to the objects themselves, not to the background group. That wouldn't make any sense. So these are static physics bodies, so that way they don't fall when gravity is instantiated. And the ground has some additional properties of friction and bounce. They're inserted in the background group, so the background group has the background, and then the ground, left wall, and right wall. Okay, so then at the end of the code is when we actually instantiate some objects. So here we're defining a variable called basket, and we're calling the constructor newBasket. So newBasket is then performing all of this code here, and it's returning the group. So basket is returning a display object, which is essentially a group that has contents we're going to adjust in a minute. We adjust the basket X and Y, so it's centered on the screen and it's 200 pixels above the bottom of the screen. Then we insert the basket into the basket group. Now I have ordered, or I've inserted these groups in a particular order. Background all the way to the back, planets in the middle, basket to the front. And this is how the planets will appear to be in the basket. So after I create the basket, then I create a table called P and then create this spawn planets function. Now let's go down all the way to the bottom. The intent here is to call the method spawn planets with a number. And what that will do is feed the number into the following. We'll create a timer that will spawn every half second the number that is fed into spawn planets. So here 20. So every half a second we are going to generate a new planet. And when we hit every half second, we'll call this local spawn method, which is a method within spawn planets. Now again, I've done this before in previous tutorials and games, so this is really should be old hat for us. So here with spawn, we feed E, which is a reference to the timer function, and so, or the timer object. Within the spawn method, I create a local variable called planet, which represents an index for the table that we created up here. Now, one note here, I am essentially using e.count as an index. If you were to adjust this so that you could destroy the planets after they were created, but spawning still needed to happen, you would run the risk of creating nil errors, because when you destroy a reference and create a nil portion of a table, it moves everything else in the table back or forward. Actually, that's a point of view thing. It moves them back, so that if it had an index of 7 and you destroyed index 6, then index 7 becomes index 6. Yes, it's very confusing, but will cause lots of errors. So just be mindful that this particular method is not foolproof if you want the option to destroy the objects while they're spawning. Anyhow, so then this planet reference will create a new planet, and the planet's X will be randomized 50 pixels to the left and 50 pixels to the right of the center. And then the Y, they'll start at the 0 of the Y. And when they're spawned, they're inserted into the planets group. And after all of them have been spawned, then we'll destroy the timer and set it to nil. Okay, that's a lot of information. Now we can focus on adjusting the physics body for the newBasket. Within the new basket constructor, we'll insert the following lines above the line g:"insert body. Local physics body, which is a table. So we're creating a new table, and then within this table, we're going to create the complex physics body for the basket. Physics body, and then open and close the square brackets and give it an index of basket. Okay, so this is an associative table. Notice that it's not numbered. Equals, open the curly brace and then close the curly brace. Okay, so we're going to nest tables within themselves, so you want to be very mindful of where the curly braces are. So this is the entire basket entry. Then open and close a curly brace, comma, open and close, comma, open and close. When you do that, then we're going to format them so that they line break. And we're going to comment. This is the left arm. This is the bottom. And this is the right arm. Okay, so don't get confused. This is one giant table that has multiple tables separated by commas. And we have used an associative index of basket, which will be important in a minute. So now the information that we put in here is the information that we will put within a standard physics body definition. So if we go down to the planet, we can take a look at the add body of the planets and see that we've got a table that represents the different properties of the physics body of the planet. So all we're doing is we're doing that for each portion of the physics body of the basket. We'll go back up. And of course, I already have code ready to go. Let me copy and paste the left side. Right after left arm, I'll paste the left arm. Let's take a look at it. I've got density, comma, friction, comma, and bounce, comma. You need the commas. If you don't have them, it'll fail and it probably will crash. And then shape equals and yet another table. Now this is where the Illustrator points come into play. I actually used slightly different points than earlier in the movie, but more or less it's the same idea. So it starts at negative 143x and negative 80y. And then the next point in clockwise order is negative 123x, negative 80y, then negative 88x, 62y, and negative 110x, and 62y. So let me copy and paste the next three portions, the bottom and the right arm. Okay, now with the three arms or the three bodies in place, we will attach the physics body to the group. We'll type physics, add body, open and close your parentheses. Remember that we're attaching it to the group, comma. Now unpack, open and close parentheses, physics body, open and close brackets, and the associative index, basket. What unpack does is it takes the contents of a table and then it'll serialize it. So we have a table here with three different entries. And so it'll unpack those entries and maintain the integrity needed for the complex physics body to work. Save it and head to the simulator and reinstantiate. And well, it's the same thing that appeared at the beginning of the movie. We have the left arm, bottom, and right arm, and then we have the instantiation of the planets over time. Now, this, excluding the long description of the previously written code, this appeared to be pretty quick. We would just define the different polygons for the physics body, pack them into a table, and then unpack them into an add body declaration. But actually it is time consuming because what you didn't see me do was write down by hand each point of the polygon that I drew in Illustrator. And in fact, there is a program that exists that allows for a bit quicker workflow with using complex physics bodies. Physics Editor is an application that allows you to import an image and draw a polygon around the image. And what it'll do is it will export a series of polygon definitions the same way that we just created by hand. We'll take a look really quickly at the basket and how we can speed up our workflow. I've imported the image into Physics Editor, and for the exporter, I'll set it to Corona. Now I'll click this star icon, which will draw a polygon around the object. Now what I'll do is choose OK, and I can begin to affect the shape of this by dragging these points and eventually create the same type of shape, although actually it'll be a little more complex. Okay, it looks okay for this particular purpose, and I'm not going to necessarily go into a physics editor tutorial except for this really quick tutorial. You can see here on the right, there's a number of options. You see, you can define the different segments. So here it's going to create a total of 15 segments. And what's really nice is that you can define the physics property for each segment. When you're done, you can export the definition. So we'll publish as, and let's place it on the desktop. We'll call it basket. Okay, so now on the desktop is the basket.lua file. And this is the result of the exporting from Physics Editor. Now you'll see it looks very similar to what we just did by hand, but there's a bit more information. What's really critical is you can see the associative index and the large table, and then you see each of the components. And it's formatted the same way that we just formatted our physics body by hand. Now there's some additional work to get the physics body imported into your project, and there are plenty of tutorials out there, and you can find them off of the Physics Editor website. But this is just to introduce you to a tool that you might be interested in investing in, and I am not being paid by these folks. I actually paid for a license myself. I find it a very useful tool and a very inexpensive tool in order to save time. For a small fee, you can download the project files for this tutorial at cheetomoskeeto.com.